3. Okay, exam 3 is about response surface, and stop me if you feel like that's not clear. Okay. First of all, you will give a global view of something. So basically, I give you a data generator from an Excel file. Okay, and it will look like something like this, okay? And
you know what you're giving out exam 3?
I actually had it done, but then I realized that there will be a lot of questions to the TA. Then I try to reformat it in such a way that minimize the argument. Okay, so something like this. Okay. I'll give you a bunch of data points. And once you have the data points, okay, you need to do two things. One thing is that, what are the two things you need to do? One thing is you need to figure out where are your four corners, right? You know, where is your corner 1, corner 2, and corner 3, and corner 4, and and say you need to figure out a center point. Okay. So where will be a good point to start? I will find a way to, for example, this graph, if I do it twice using the same data set, and I want you to find one minimum, one maximum, okay? And then I'll say you need to find a same starting point. Where you want to start? Somewhere around this blue area, right? But going upward or going downward, there will be some local trap. And you don't want to get trapped. You want to keep climbing so you can go to the max, and keep going, you can go to the mean. Everybody agree? Agree? And next thing is that just like previous exam, to prevent you copy-paste from somebody else's answer, I will always give you some random number generator to oscillate this whole thing. So even though you will have similar path, shouldn't be exactly the same. Agree? Okay. So the problem is, okay, you need to find a starting point, and then you need to find a way to define four corner, and center point you need to sample 3 to 5 times. So totally you will start with 9 data points. Agree? Or not 9 or 7, 4 plus something data points. Okay? So everybody should be able to collect, find a starting point and generate those points. And then say, okay, now I have my 8 data points, and I can plug them into my SAS to get the ANOVA and for the directions. So far, so good? Yeah?
So you talk about getting multiple data points for the center point, and that makes sense to me in terms of like a real world experiment. How does that work in this case where we have the example?
Well, first of all, you have your data point, right? And then I would say that, based on, I'm going to show you immediately. You start from here, then you say you're going to move to 0.7 or somewhere. Okay. Then that will be your new center point. Right. And then you need to build a new cage. Okay. And then you get to that new cage, and then you figure out what are the 4 corner points and what are your center points. You calculate, technically, you should move square by square, gradually get closer to the max. And then I will make the problem. I say that, okay, for the mean, let's flip it upside down this way. So the mean upside down will be also a max, right? Max become mean, mean become max. So you can use the same algorithm to find those data points, okay? And your job really, everybody can do it. Just like previous exam, everybody can do it. The thing, what is the intelligence or what you call real world situation here is if you define, okay, what will be a situation for you to be excel in the real world? Your step size or your square, not too big, not too small. Because if you have a square huge, there's a possibility you over the red and drop into the blue again. So you didn't even know there's something good in between, right? But in this case, well, that's one thing different. In the real world situation, I just want to make sure my mic is on. Yeah. In the real world situation, are you going to have this map for you? No, all you have is just experiment, collect 4 corner points or a bunch of center points, right? Actually, you asked another very important question. For the exam or for our class, I don't want to make it too hard, so it's always x1 and x2, x1, x2 square and x1, x2 interaction term. In the real world situation, every time, are you going to really having a 2x2 with a center point situation? Could be our exam 2 situation, right? A variable. And if you have a variable, imagine that you have to do 256 cube to create a direction. That would be too much, right? So in the real world situations, you could have a very complex fractional factorial design. Can everybody visualize this? In the real world situation, you could just kind of repeat your exam 2 square by square. You run a 2 to the a minus 3 design, figure out which way to go, which way is max, getting bigger value, and move to another one. Is that possible? Yeah, so you guys with me? Is for you to appreciate a response surface. That's why I make the problem this size. But in the real world situation, like right now, the pharmaceutical company, their big data experiment, a lot of time is 2 to the 12, 2 to the 13 minus who knows how many. It's a huge experiment, but they also try to figure out that how to do a fractional factorial design to make it small, okay? So, no problem here, right? For the exam, it's 4 corner, center point, plug it into SAS, find another center point, plug it into SAS. Agree? But in a real world situation, your square or your cube can be very, very fractional factorial design complex. Agree? Okay? And everybody should also agree that no matter what, whenever I give you a 2x2 experimental design, you can have a regression view, the beta 1, beta 2 for your parameter, but you also can have a ANOVA view, know where is your overall mean and everything. So we can consider we're doing everything exam 1 and exam 2 repeatedly. Except that here I just try to minimize that complexity so we can focus on this piece. Okay? Show hands. You fully visualize you will have a response surface like this. You find a 2x2 cage. You find your center point. You find your cage size. And then you will have every step, every run, every iteration, you will have 4 corner plus 3 or 4 corner plus 5 center points sample out of this. And the other thing is that since I give you the function, right? See here, you have the function of these things. Can I make this function, what I'm saying is you can create this response surface any way you like, right? Okay, question.
I was just clarifying, so when we start finding our first point, we start at the 0, 0 coordinate?
No. You decide where, anywhere. And of course, the questions, I will find a way. See, since you can look at this, right? So if I say find a max, if you start right at this 4 top, you don't need to run any more iterations, right? But here's the problem. I'm going to say that, you can start from here. If you want to cheat, you said, hey, I have domain knowledge. I'm going to start from here. But then I flip this problem upside down. You're going to travel from this starting point to find this mean without a lot of travel, right? You follow me? So, but you can start from here. Then you have a lot of travel here. But so what would be a good thing to start was probably somewhere in between, right? So now you have minimum number of investigation here and minimum investigation here. But what will be the other concern is you get trapped in the local green zone. You're in a green zone and kind of like, hey, no matter I look at it, it's stable. And so how to get out of that trap? That makes sense to you? Yeah. But those are the agenda for response surface I would like to emphasize.
So we want to pick like a logical starting point.
Yeah. And does that reflect the reality? Even you have, say, in reality, the cage size is 2 to the 13 minus 5. Still, right? That part of the consideration is based on your understanding about the real world. It basically said that where I can gamble for good luck of success. Yeah, I'll give you one good example. Do you guys know what is slot machines in Las Vegas for gambling? And even though people say it's IID independent, but if that machines, okay, just bing, 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 come up with a bunch of big prize, would you invest on the machines again? Most likely not going to have another run pretty soon, right? How many of you ever seen the movie Counting Cars? A bunch of MIT grads and an MIT professor, based on a real story on how they play blackjack by Yeah, it's a real story. Actually, it happened when I worked at Liberty Mutual because it was a big scandal at the time. So what I'm saying is you are trying to gamble in the real world, okay? And see, if you say, I'm going to play cheap, I'm going to start from here. One step, I'll find the optimum. But if you start from here, then the price for you to come down will be hard, right? So if we're saying that this is a investigation, you basically need to find your starting point, your base station, somewhere in between, so it can be easy both ways, okay? This is just for you to this is not the exam problem. This is originally the exam problem I planned to use, but I decided not to use any one of them right now because I know if I give you any of this, the TA gonna receive tons of email for. Yeah. And here's another one. You know where is the peak, and where is the valley. And the problem, I'll probably say that, hey, investigate to get good solutions, find one peak, find one valley. But then I will say that, okay, give you extra credit if you can find second peak and second valley. What I mean by that means that you find a point that you can get a lot more other stuff. Because next week, I probably will start talking about what is Taguchi design. It's robustness. Means that a good answer insensitive to a lot of stuff. Okay? Okay. So, next, I would like to talk about the is this the one? Okay. No, this is another one. We'll see. Oh, there's another one. Yeah, here we go. Okay. Now you can use the Excel file to find your data points. Okay, and I will add enough random noise for you, so your surface at least will be a little bit different from others' surface in detail. Okay, and then your job at the beginning is always find 4 corner points and 5 center points, or some center points to review, to go further. Okay? What's the benefit of having more center points? You have more consistency to know for sure. But then you waste 2 more data points, okay? And, okay, next things. Can you turn your problem into, if you sample 8 data points, you can use Excel, but you can also use SAS, okay, to find a regression, intercept, and too slow. Agree? Okay. When everybody see that, you can do that, right? Yes, no? Okay. Next, if you can find those things, okay, we can do it in Excel to calculate the residual, the interaction and the quadratic terms. For you, if you start with a good starting point, okay, you shouldn't have any interaction term or quadratic term a lot. Because every time when you have interaction term and quadratic term significant means what? Could be the peak, convex peak or concave valley, convex valley or concave peak or a saddle point. You don't want the saddle point, so you can keep moving forward, okay? And now let me show you the Sas Code to do that, okay? Here is the Sas Code for you to get that done. Response surface, natural start. Okay, we'll use this one. Okay. Open. Download. Where's download? Oh, here we go. Okay. People, look at here. Your handout got 4 corner point and 5 center point, coded in their natural variable, coded as positive 1, negative 1, and then you have 4 corner measure and 5 center measure. See that? And look at the SAS. You have the same things. 4 corner measure and 5 center measure. Okay? So, worst case, you don't even remember what to do. All you need to do is just copy those 9 data points from the Excel, step by step, plug them in, and once you plug them in, okay? Here I'm showing you several different ways to model this. One is just using GOM. Since there's no class variable, model equal to y eta 1 eta 2. That means what? Model that just like a regression. Or you can model that using RSREG, is response surface REG. Okay? You can plot the prediction, and then you can plot the response surface, and you can plot the REG regressions showing the leg of fit, okay, in a 3D surface. So you can look at it and say that does this represent what I'm thinking about that surface? And finally, okay, you can plot all of them. So in other words, is that this program can be used again and again and again every time you pick up 9 point. Agree? Let's run it. Okay, and when you run it, okay, this is the last picture you will see, and you will like that picture. Why you like that picture? See that it's kind of like just, hey, this is linear, right? So you know that, see here, going that way is 40, 40.5, 41, 41.5. Coming this way is 39. So you know that if I'm looking for max, which way should I go? This corner, going that directions. And of course, I'm going to show you how to calculate that angle. But no matter what, this is the angle for going up, this is coming down. Okay? And I give you all the residual analysis and said if that normal or not normal. But most important things you need to figure out is this. Look at the equations here. Linear term. Significant or not significant? Significant, right? P-value less than 0.05. And that is exactly the same as the ANOVA table here. It's significant. And then all the quadratic term, 0.81, 0.82, interaction term and quadratic term, not significant. That's good news. That means that you still have place to go to climb. So now back to the Excel problem right now is if you start from a good point, means what? Improvement, improvement, improvement. The other side is improvement, improvement, improvement. And what will be bad for you is if you define your cage too small. This is the argument I keep talking about in our previous experimental design part. If you define your cage too small, that means what? Your exam 3 gonna take days to finish because you will have trial after trial after trials. And now you're wasting is your time. But in the real world, you're wasting is your boss money. Okay? So that is the part like, now we're on a fair, even plane. Whatever I have, you have. You just need to figure out how big or how small you want to do. So basically, you want to find the max and the mean as quick as possible, right? We're on the same page now? So this, and here, I'm showing this in a 3D plan. Can you tell? This is levels that you can keep increasing and decreasing for max or for mean. There's no, did you see any stationary point here? No peak, no valley, no saddle point, right? That's, keep going, keep going, keep going. And this is the color plan is same things. Keep going, keep going, keep going. Okay? So this is the first Sas code you're gonna use again and again to investigate, find your direction for growing and shrinking. Problem? No problem. Anybody download the Sas code right now? And you don't change anything, okay? All you need to do just plug in, oh, here, let me show you. If you said, I'm lazy, I don't want to use 9 data points, okay? I'm 5 center point. I'm gonna delete 2 more, okay? So I'm just delete them for now, okay? And let me just kill the outcome. Okay, now I'm doing is 3 center points, okay? And let me clear the log. Okay. You still can run it. It will still give you, it's a flat surface. Well, actually, if you look at a little bit, did you see that because you only have 3 center point, that plan kind of warp a little bit? But they're not too bad, right? You still can figure out your directions. Okay? So let me ask you this. For your exam, since you can get those numbers through random number, what will you do? 3 points, 4 points, 5 points? You decide. Okay? Yeah?
What would you recommend be like our number of center?
What?
How many center points would you recommend for us to get accurate data?
After what?
How many do you want? Like if you say we can pick however many, like
Well,
3 or 5, like
3 to 5.
okay.
Yeah. Don't go beyond 5, and don't go under 3.
Okay.
Yeah. For this for this kind of experiment. Well, let me put it this way: if say today this is a real world situation like our exam 2, we do that again and again, I will have a lot more center points. I probably will have more than 20 center points because there are so many possible. You follow me? You have this way, this way, this way, so many ways you can investigate. Okay? Until I kind of feel, oh, this is stabilized, then I'll have less data points. Okay?
So just a quick clarification. Did you say that for the extra center points, we are generating them randomly?
Well, no, because every time, here, back here. Since I will give you a response surface and let you add random number on it.
Okay.
So every time you click on that data point, say I need this center point,
Okay.
you will get a new number, right?
I gotcha. Yep.
Yeah, so it's kind of not like, try 1, try 2, try 3, you will have the same number. It will oscillate a little bit,
Okay,
right? Because we have that local commute.
yes.
Make the 5 data points kind of like jumping
Yeah,
over.
I understand now, I just didn't understand the
Yeah.
mechanics of these.
Well, the only thing is that you want to make sure that a 4 corner point, you can lock it.
Right.
Yeah. Okay. I will give you the specification how much noise you need to add, because if you add a noise is kind of like 0.00001, the surface will be extremely smooth, and then there's no need for the center point. Okay. Next. Okay. Once you have that center point and everything's, okay, you know that, okay, the quadratic is not significant and that is not significant, and now to move away, okay, the point from your 0, 0. So you have to say that, okay, I need to move how close or how far, and those is based on this, okay? Here is the parameter. Go back to the SAS. Remember, I have 2 different regressions, or one is based on the coded variable, one is based on the actual variable, but it's same regression. But the coded variable itself, the 0101, actually will tell you which way to move. See here, the parameter is 0.775 x1 and 0.325 x2. That means that every unit of x1 I add, and every unit of x2 I add, will move the y 775 plus 325. Everybody sees that? You see that?
I think so.
Huh?
I think so.
Okay. There are 2 regression, right? One is natural variable regression. One is the coded, moving this wall. That's your x1, x2 regression. The x1, x2 regression, let me double check, make sure you have it. Now, reaching this stage, okay, I hope you have a good comprehension about experimental design. Now I'm just saying that there are a lot of detail. You mess up one step, you will, it's kind of like domino effect. You guide yourself in the wrong directions, and you will see the map. You're getting worse and worse. You're not climbing the mountain the right way. You guys follow me? Okay? And that's another thing, is why I'm so careful about this. You need to get it right now. Don't bother the TA said that, show me an example, give me another things. You should be considered this is a real world situation, you on your own, okay? Don't ask the TA for extra help once you start your investigation, okay? Here. When we run this, okay? I know. Watch here. For the starting point of this, okay? Watch what I did carefully. Control H, okay? Change eta to X. Okay? Now I'm running the regression based on here. The input I have x1, x2, and here I need to change it back. Eta 1 and eta 2. And then I can have eta 1 and eta 2. Look at the data set. I have the natural eta 1 and eta 2, x1 and x2, based on your Excel. 4 corner and the response y. Okay? And then if you're using eta 1, eta 2, you are talking about your regression based on, or your ANOVA table based on the natural variable. But if you run it as y1, x1, x2, x1, x2, you're running this experiment based on what? The coded variable. Okay? It's the same program, just which one you want to base on. So let me run this one more time so you can see that. Okay? Okay. So now, see the whole thing is running based on x1 and x2. Okay? 4 corner is this. Okay? And then when you look at the estimate, people pay attention to the estimate. Estimate is what? The directions from your coded variable. Which way should I go? Should I go for 1, 1? Or -1, -1? Or +1, -1? Should I go in any 4 corner? No. The direction I'm going to go will be what? 0.775 in x1 and 325 in x2. Okay? Young lady, why that's the direction I should go?
Which young lady?
Well, okay, of course it's you. Which way should I go?
I'm not sure.
Because you don't care, or I didn't make it clear?
Because I just wasn't paying attention enough.
Say that again?
Because I wasn't paying attention enough to know which way to go in this particular instance.
Okay. Now, then let me repeat that one more time, so maybe we can maintain the understanding of this classroom. Okay, the regressions got 2 different ways. Natural variable and coded variable. Okay? And then using coded variable basically is +1, -1, 4 possible corner. Agree? And then I can say that, okay, go which corner? I'll have bigger value. And if I just want to do that, I can just look at Excel and say which corner will be bigger. But if I'm using regressions of the coded variable, the coded variable basically shows this. Regression y equal to the intercept plus x1, but not -1, not +1, is 0.775 of x1. So I should every x1 I increase, I will have 0.775 improvement of my y. And x2 will be 325. That's the regression of my beta 2. So similarly, the SAS will tell you, here is your estimate. Center point, moving this much will improve your x1. Moving this much will improving your x2. That is the direction for your response surface. Okay, show hands. You get it or you don't? Okay?
I just have a question.
Good.
So, I'm struggling how to phrase it.
Make that clear, because I don't, what I'm saying is, this is like riding bicycle.
Yeah.
This is the very end. You need to know either you can ride a bicycle, you can swim, or you cannot swim. I don't want you to get out of this class and say that, you know what, he's nagging, but I don't get it. What's the point of doing this? The response surface will be something you will encounter for your senior design, for your real world situations. Sooner or later, this is not statistics, this is not optimization. It's a real world situation. So elaborate that what is the concern, because I want to make sure that you get it.
So when you're talking about a direction,
Mm-hmm.
say I take my x1 and my x2, and that will give me a point on that grid.
So yes, so you basically here. I think I get your point. Is this? I'm gonna move one step of x1 and one step of x2, right?
Yes.
If I do one step of x1 and one step of x2, plus 1, then I will only move y with this much of improvement. But look at the picture, okay? We know that what we really want is here. If I'm going straight up, 1, negative 1, 1, negative 1. So if I'm moving in this four corner, I'm not really moving against the perpendicular of this. Would you like to climb the stairs in the direction this way? You follow me?
Yeah.
Yeah. So that's the points we try to climb. Okay. Let me keep that thought in mind for 1 second. See if this will help. Okay. If I'm start doing this, okay, and every step of my x1 and x2, I'm just saying that, oh, because you say 1, 1, 1, I'm just 1, 1, 1. Then I'm not going to get as much y as I want. So look at here, what happened is that if I let x1 be 1, x2 is, remember, it's 325 over 775. Now, if I let this be 775, this will be 325. But if I say that, oh, I'll let you push x1 is the one with good improvement, right? I say x1, you go all the way. So x1 move to 1. If x1 move to 1, x2 can move a little bit, push all the way. How far can it push? 0.335 over 775. So x2 push to 0.42. And then now we can say that, okay, let's move next step. So now x1 move to x2 to 2 to 3, and every time when you move, you can improve that that points. See here, double, double, double. But when you stop, is watch here. If you look at a y value, okay, it's getting better, getting better, getting better. But sooner or later, it drops, right? So why it drops? Or a potential optimum point, right? So, Kevin, if I pass, I drop. Okay, Kevin, you with me on grow. So this thing's grow, and my value of y is getting bigger and bigger and bigger until I start dropping, right? So, at this point, what will be your speculations legally? You say that someone says that this is the best medicine.
Well, it could possibly be the best. I still know yet.
Say,
Well, I mean, it could be the best, but actually, I don't know yet. They'll probably need to do a little more testing.
good. So you basically said that, I have a hunch. This is a good point, but I need to double check, triple check, right? Make sure this is not an accident. So how are you going to check here? You need to stretch out a little bit, because if you stretch out, keep looking, and then you say that I'm the max. No matter which way I keep looking, everything is smaller. Then you know that probably that's a real max. But if you stretch out a little bit, you see another climb. What do you know? Maybe that's a local max. There's something bigger after that. You get it? Okay, Victoria, your turn. Sorry, I noticed you want to ask something.
Yeah, it was a clarification, and I think I'm still kind of confused.
Okay.
But that our takeaway? Is that our takeaway from looking at the estimate?
Oh, you mean from the SAS?
Yeah.
Oh, okay. Here,
Is it because
we're gonna format. I'm gonna format all the problem for max. So min problem, you need to flip it to become max. Okay. So the regression here is 40 plus 0.775 times x1 and 0.325 times x2 plus the noise. Agree? Okay. So what does it mean? Is every unit of x1 can improve x1 by this much, and every unit of x2 can improve the y by this much. Agree? Agree? Okay. So technically speaking, would you agree with me that improvement of x1 and x2 are not equal power? Which one got more power to improve improve y?
X1.
X1. So I should invest more on x1, right? So every unit of x1 I improve, x2 said, hey, that's not fair. I also want to have one unit. You will say what? Here's the evidence. You can only have a proportion of x1. And what will be the proportion? 0.325. Here. So you will go 0.325 over 0.775. Yeah. So it's 0.325 and 0.775. Okay? And yeah. I can give you everything, but here you know that every x1 I have, x2 can only have 42%. Otherwise, I overinvest.
So that's saying for our next move.
So next move, you're doing the same things. Find a center point, find 4 data points, you find...
So we would move 1 in the x1 direction and 0.419 in the x2 direction.
Right.
And then that's our new point.
Your new center point. And then at your new center point, because in real world, you need to collect 5 more data points. And that could oscillate a little bit, and then you have your 4 corner. You need to figure out, hey, am I in the right place? Which way to go? Is that clear now?
Yeah, that makes, I'm getting there, yeah, that makes sense.
Okay. No, I'm not trying to, I'm just trying to say that let's mentally walk through this, see is anything missing. I don't want to, I said, oh, it's okay to go. And then the minute you getting the exam problem, you start saying that, oh, I don't know what to do here, I don't know what to do there. Okay? Yeah. I would rather you grill me now. Don't grill TA once I give the exam.
I think I'm following so far.
Okay. So let's okay. You know what? I'm gonna have Howard. You're with me? Okay. Mentally, you tell me. I give you a response surface like this. What's your first step? Find a center point. So we find a center point. And how you find that center point is a center point easy to climb, easy to go down. Next steps. Young man, your turn. And then you decide your step size, because once you decide your step size, you can decide your 4 corner point.
And you want the step size to always be between 3 and 5, right?
Step size between what?
No, 3 at the minimum, 5 at the maximum.
Well, 3 to 5, but you know, when you have the jump on the real number, you can make it really, you know, this is spreadsheet, right? You can make it huge. You can do it. All you care about is here, what I'm saying is, the number here dictate where is your 3, where is your 5, right? You follow me?
Yeah.
Yeah, the steps are, and, okay, for convenience, we'll say, yeah, 3 to 5 is a good way to think about it, because that way you know that from here to here is 0 to -1, 0 to +1, from here to -1 to +1. Agree? Yeah. So, what's your question? So you have 4 corner point, and then you need to sample your, see here? Because I'm using random number, here, there's a trick you can do. Just watch the center point. See, every time I click, the center point right now is 1.43, right? If I do a Control S, it's 1.83. I do another Control S, it's 3.75. I do another Control S, is 1.9. You follow that? Every time you generate, you only sample the 4 corner point once, but you sample the center point 5 times, 3 to 5 times. Okay? Now you have 9 data points, and you can turn those 9 data points into SAS with natural variable and coded variable and response. And then this is basically just running regressions, and this regression will have the quadratic term, interaction term, or determinant. So look at here, okay? You can have the linear, you can check the quadratic term, you can check the interaction term. You can check x1, x2, x1 times x1 square, x2 square, x1, x2 interaction, and x2 square. Okay? And the sum of this really is the sum of square of everything. Okay? And I just give you 3 different ways to view this. Is that clear? Yeah.
Can you show us how you would do like the first quad? Like how do we start with like putting it in SAS? So can you show us like how you do like the first
Fine.
square and then do like another iteration of that? So like starting square and then do one more step. So we can
Okay. Let me just do this. Okay? First time I find a 4 corner. Okay? So I just write down, let me do this. Let me cheat a little bit. Okay? Let's just pretend this is the, because I don't want to spend time typing. So here's my eta in this. But now I just need to turn them into different value. Okay? So this is my natural variable, 4 corner, and my coded variable, 4 corner, and here is my center point, 9 points. Okay, so far so good? And then let's just do a Control S. Okay, now I have the 4 corner. Okay, and let's say that here is -1, -1. It's 2.05. And oops, shoot. Let me do this. Control C. Paste special. Value. Lock the value. So let's do this. 2.02. Corner 1. Okay. And then corner 2. 3.11. Corner 3, 2.13. Corner 4, 1.9. And then for the center point, first time is 1.32. Okay, 3.26. Okay, and then 4.15. 1.53. 1.12. So I run a 2x2 experiment using this response surface. Get it? Get it? Yeah? Now you have your 9 points, okay? And of course, this you should supposed to check where is your true eta, where is your x1. Okay? But once I have this, put these things back into your SAS, and we're supposed to start climbing. Okay? And then you run this. Okay, but because I'm just randomly pick the point, so you know this is what? Your quadratic term is not center. It's not, this is not, did you see a plan? No, you don't see a plan here, right? You see, oh, this is a nice saddle plan, right? So that means what? Tricky. It's time to, Kevin, it's time to stretch and investigate more about the local detail, right? Right?
Yeah.
Okay, so now you cannot just say that, well, I don't want to do that. I want to just keep going. Because when you have this, one way up, the other way down, which way is the right way? So we need to stop for a second, agree? To know, if there is another local point to use. But how to plug in the 9 data points? Is that a problem to you now? Okay.
Wait, can you go back for 1 sec, sorry?
It's to Excel or to SAS?
To Excel.
To Excel, okay.
So I got the corner points,
Right?
but then the first one you move into, that's 1.32.
Uh-huh.
Where did that number come from?
Oh, it's when I copy from here. Okay. The 4 corner you have no problem, right?
Yeah, I see those.
So the 4 corner is -1. So basically, probably my -1 is here, my +1 is here, and then I have my -1 here, my +1 here, right?
Yeah.
So the 4 corner, no problem.
Uh-huh.
And so the 4 corner points got locked. Now the question is, everybody he's asking, where are those center points coming from? The center point should be from here, right?
Yeah.
So what I did is every time so read the value I have right now, 3.15, right? Right? First center point. Don't use this one because I only copy paste value.
Up there, 2.2, 3.15, yeah, that's the number.
Okay, that's the first one. Okay, so I put 3.15. Okay, and then when I hit return, see I can have another sample now? Since I add a random number in. What's the second center point? 4.19, right?
Okay, yeah.
Well, why I copy paste value here? Because the 4 corner I want to lock. I don't want to keep sampling the 4 corner.
So now you want 4 random samples of the center point.
I know 5 or 3 or 3 to 5.
Okay.
Make sense?
Yes, I missed that, sorry.
No problem. Yeah. I just want to make sure that
Yes.
this time we are on the same page. Okay, so everybody know how to sample 9 data points from my problems. This is fake. This is science fiction. Okay? In a real world situation, you basically run a 2x2 experiment with 5 data points. You basically need to cook whatever chemical, drive whatever car for getting those 9 data points. I'm just creating a Excel for you to generate those data points. Once you have the data points, you can use our old Excel to figure out the regression, figure out the center station, and everything. But remember, I said that's too much work. Let's just let SAS do it. So you plug those things in. And remember, I already told you, if you let Y model equal to eta, means that you're doing the regression based on the natural variable, because eta is how you generate your response surface. But you can also use the square dance, the coded variable, to generate the directions. And so you plug those numbers in. Okay? So let me do this here. So if I plug in those number, and when I run it, what do you care? What do you care? So what? First thing first, you look at the landscape and say that the landscape, is there any improvement directions? Or you have a local stationary point. Okay? And if you look at it, it says that, oh, this still got something to grow or something to shrink. Then you need to figure out which direction, how much, right? So you look at the estimate, 0.775 and 325 of those x1 and x2. But you look at those directions based on what assumption? The quadratic term and interaction term should be significant or not significant?
Not significant.
Because if it's significant, then you need to investigate now. If it's not significant, it means that we still have place to go. Agree?
Yes.
Okay. So you will grow, shrink, and keep climbing. And here is the book says that you climb 10 times, you pass an investigation point. That is the time that you document your why and say that good, well, not good. Then you know that you have a peak. And once you have the peak,
Stop for good, though.
huh?
How would you ever know when to stop?
Well, the questions I will answer again in two different ways. One is the way in the exam. One is the way in the real world. Okay? Okay. In the exam, you know the landscape. So if you know roughly, here, you can just type max. Find where's the max. You say that max should be here. Yeah, I can do this. Max. Just for one trial. Okay? Okay, where's my max? That max value is 11.6. Okay? So you know that you would like to get as close to 11.6 as possible, right? Right?
Yeah.
So in the exam, I actually give you a cheating tool, kind of like, hey, if you're not there, you probably need to find another starting point to keep going. Okay?
Yeah.
In the real world, okay, that is where the stretching point coming in. Sometimes people just stretch a little bit. Sometimes people will stretch a lot more to make sure that you're not wasting your time. Okay? And another things people trying to do these days is they use MATLAB simulation to generate tons of different chemical combinations. So in other words, they don't use Excel. They just use whatever they know to generate some synthesized data to figure out that, let me put it this way, kind of like you play gamble in a certain way, and it says that, at least I 99.999% of the time, I don't get anything here anymore. Maybe it's time to stop. Okay? But statistically, we're using the stretching point to do the check. So let me show you the stretching point. You keep grow, and once you say that, oh yeah, this is the proportion you need to do, and now you're basically said that I need to find an eigenvalue and an eigenvector to decide if I want to keep climbing or not. So if you have the quadratic term, Okay? If you have the quadratic term. In other words, the whole regressions is beta 1 and beta 2 is your linear term. Agree? You don't need to have beta 3, beta 4 because we make this only a cage, a square. And you have a beta 1, 1 is the x1's quadratic term. You have a beta 2, 2, that's the x2's quadratic term. You have a x1, x2, that's your beta 1, 2, that's your interaction term. Okay? And so you put this into a matrix. Okay? And we call this a quadratic form. This is basically remember your high school algebra, ax squared plus bx plus c, and then how do you know it's convex or concave? There is a determinant check, it's b squared minus 4ac, greater than 0, smaller than 0 things. Here is that in a matrix form. It will equal to this guy. So your stationary points equal to B inverse times B. And then your stationary point can be expressed for your y performance equal to beta 0, either intercept plus half of your stationary point times B. I'll give you a numerical example so you won't get confused. But this stationary point could be convex, could be concave, could be a saddle point. Okay? Now, how can we find that point? Yeah, 5 minutes? Okay. To find the points, now we need to make our data with 4 more stretching points. For the exam, your stretching point is square root of 1 plus 1. So always, your cage is 1, 1, right? So your stretching point is 1.4104, square root of 2, square root of 2. Here's 1, that's negative 1, right? So I need to get outside the wall and to check. So the outside of the wall is positive 141, square root 2, square root 2. So now you need to sample 4 more data points than your original experiment. If your original experiment is a square, now you need to say what's outside that square. Okay? So in the case here, you need to get out a little more. So if this is 0.5, so here, in reality, this data point, okay, that is not 1.414. That point is 1.5, right? Right? So you know that you can linearly interpolate where is 1.414. It's probably just a little bit less than that. I'll show you the linear interpolations next time. But now let me show you how to run it in SAS. Okay? How to run it in SAS is this. Okay? The check, RSM final. Okay. So okay. So now where's down low? Here we go. Okay. The code almost the same as before, except this time, can you see that I have, this one I just have 3 different responses, okay, rather than 1. But can you see that you have, if you only pay attention to Y1, ignore Y2 and Y3, can you see that I have 4 corner point, 5 center point, and 4 stretching point. And the stretching point code is 1.414, square root of 2. Can you see that? And then once you see that, all you need to do, okay, is run this. Not only will show you the shape, it also will tell you the eigenvalue and eigenvector for the your stationary value and everything. Okay, so originally I was planning finish all this and give you the exam problem this weekend. I think I probably will still do that, but some of the final investigations I probably need to cover that next Monday. You follow me?
Yeah.
Yeah. But if I give you the exam problem now, at least you should be able to start play with the the initial points.
When is it going to be due?
Your final day. Yeah. Yeah. And for the grad student, your term projects, same thing, due at your final day. Okay? Yeah. Don't underestimate the complexity of this, okay? The devil is in the detail. The devil is in the detail. Sometimes it looks really easy. The minute you start playing with it, you'll start saying, oh, holy cow, there are so many problems.